let's talk about AI a little bit if we could. So maybe a good entry point is just talking about computer-assisted proofs in general. Can you describe the lean formal proof programming language and how it can help as a proof assistant, and maybe how you started using it and how it has helped you?
So Lean is a computer language, much like sort of standard languages like Python and C and so forth, except that in most languages, the focus is on producing executable code. Lines of code do things. They flip bits, or they make a robot move, or they deliver you text on the internet or something. So Lean is a language that can also do that. It can also be run as a standard traditional language, but it can also produce certificates. So a software language like Python might do a computation and give you that the answer is 7. Okay, that it does the sum of 3 plus 4 is equal to 7. But Lean can produce not just the answer, but a proof that how it got the answer of 7 as 3 plus 4, and all the steps involved so it creates these more complicated objects, not just statements, but statements with proofs attached to them. And every line of code is just a way of piecing together previous statements to create new ones. So the idea is not new. These things are called proof assistants. And so they provide languages for which you can create quite complicated, intricate mathematical proofs. And they produce these certificates that give a 100% guarantee that your arguments are correct if you trust the compiler of Lean. But they made the compiler really small, and there are several different compilers available for the same.
Can you give people some intuition about the difference between writing on pen and paper versus using Lean programming language? How hard is it to formalize a statement?
So Lean, a lot of mathematicians were involved in the design of Lean. So it's designed so that individual lines of code resemble individual lines in a mathematical argument. Like you might want to introduce a variable, you want to prove a contradiction. There are various standard things that you can do, and it's written so ideally it should be like a one-to-one correspondence. In practice, it isn't, because Lean is like explaining a proof to an extremely pedantic colleague who will point out, okay, did you really mean this? Like, what happens if this is 0? Okay, how do you justify this? So Lean has a lot of automation in it to try to be less annoying. So, for example, every mathematical object has to come with a type. Like if I talk about x, is x a real number or a natural number or a function or something? If you write things informally, it's up in the context. You say, clearly x is equal to, let x be the sum of y and z were already real numbers, so x should also be a real number. So Lean can do a lot of that, but every so often it says, wait a minute, can you tell me more about what this object is, what type of object it is? So you have to think more at a philosophical level, well, not just sort of the computations that you're doing, but sort of what each object actually is. In some sense.
Is it using something like LLMs to do the type inference, or like you mentioned with the real number?
It's using much more traditional, what's called good old-fashioned AI. You can represent all these things as trees, and there's always algorithm to match one tree to another tree.
So it's actually doable to figure out if something is a real number or a natural number.
Yeah, every object sort of comes with a history of where it came from, and you can kind of trace it.
Oh, I see.
So it's designed for reliability. So modern AIs are not used it's a disjoint technology. People are beginning to use AIs on top of Lean. So when a mathematician tries to program a proof in Lean, often there's a step, okay, now I want to use the fundamental theorem calculus, say, okay, to do the next step. So the Lean developers have built this massive project called Mathlib, a collection of tens of thousands of useful facts about mathematical objects. And somewhere in there is the fundamental theorem calculus, but you need to find it. So a lot of the bottleneck now is actually lemma search. There's a tool that is in there somewhere, and you need to find it. And so there are various search engines specialized for Mathlib that you can do. But there's now these large language models that you can say, okay, I need the fundamental theorem calculus at this point. And it'll say, okay, for example, when I code, I have GitHub Copilot installed as a plugin to my IDE. And it scans my text and it sees what I need. It says, I might even type, okay, now I need to use the fundamental theorem calculus. Okay. And then it might suggest, okay, try this. And like maybe 25% of the time, it works exactly. And then another 10, 15% of the time, it doesn't quite work, but it's close enough that I can say, oh, yeah, if I just change it here and here, it'll work. And then like half the time, it gives me complete rubbish. So, but people are beginning to use AIs a little bit on top, mostly on the level of basically fancy autocomplete. That you can type half of one line of a proof and it will tell you.
Yeah, but a fancy, especially fancy with the sort of capital letter F, is removes some of the friction
Yeah.
mathematician might feel when they move from pen and paper to formalizing.
Yes. Yeah. So right now I estimate that the time and effort taken to formalize a proof is about 10 times the amount taken to write it out. Yeah. So it's doable, but you don't, it's annoying.
But doesn't it like kill the whole vibe of being a mathematician?
Yeah.
Just
So, I mean,
having a pedantic coworker.
right. Yeah. If that was the only aspect of it. Okay. But, okay, there's some cases where it's actually more pleasant to do things formally. So there's a theorem I formalized, and there was a certain constant 12 that came out in the final statement, and so this 12 had to be carried all through the proof, and like everything had to be checked that it goes all these other numbers that had to be consistent with this final number 12. And then so we wrote a paper through this theorem with this number 12, and then a few weeks later, someone said, "Oh, we can actually improve this 12 to an 11 by reworking some of these steps." And when this happens with pen and paper, like every time you change a parameter, you have to check line by line that every single line of your proof still works. And there can be subtle things that you didn't quite realize. Some properties on number 12 that you didn't even realize that you were taking advantage of. And so a proof can break down at a subtle place. So we had formalized the proof with this constant 12. And then when this new paper came out, we said, "Oh, okay, let's." So that took like 3 weeks to formalize, and like 20 people to formalize this original proof. I said, "Oh, but now uh, let's update the 12 to 11." And what you can do with Lean is that you just in your headline theorem you change the 12 to 11, you run the compiler, and like of the thousands of lines of code you have, 90% of them still work, and there's a couple that are lined in red. Now I can't justify these steps, but it immediately isolates which steps you need to change. But you can skip over everything which works just fine. And if you program things correctly with sort of good programming practices, most of your lines will not be red. And there'll just be a few places where if you don't hard code your constants, but you sort of you use smart tactics and so forth, you can localize the things you need to change to a very small period of time. So it's like within a day or two, we had updated our proof. Because this is a very quick process. You make a change. There are 10 things now that don't work. For each one, you make a change, and now there's 5 more things that don't work. But the process converges much more smoothly than with pen and paper.
So that's for writing. Are you able to read it? Like if somebody else sends a proof, are you able to like what's the versus paper and
Yeah, so the proofs are longer, but each individual piece is easier to read. So if you take a math paper and you jump to page 27 and you look at paragraph 6 and you have a line of text of math, I often can't read it immediately because it assumes various definitions, which I have to go back and maybe on 10 pages earlier this was defined. And this, the proof is scattered all over the place, and you basically are forced to read fairly sequentially. It's not like, say, a novel where, like, in theory, you could open up a novel halfway through and start reading. There's a lot of context. But when a proof in Lean, if you put your cursor on a line of code, every single object there, you can hover over it, and it would say what it is, where it came from, where stuff is justified. You can trace things back much easier than sort of flipping through a math paper. So one thing that Lean really enables is actually collaborating on proofs at a really atomic scale that you really couldn't do in the past. So traditionally, with pen and paper, when you want to collaborate with another mathematician, either you do it at a blackboard where you can really interact, but if you're doing it sort of by email or something, basically, you have to segment it. So I'm gonna finish section 3, you do section 4, but you can't really sort of work on the same thing collaboratively at the same time. But with Lean, you can be trying to formalize some portion of the proof and say, I got stuck at line 67 here. I need to prove this thing, but it doesn't quite work. Here's the 3 lines of code I'm having trouble with. But because all the context is there, someone else can say, oh, okay, I recognize what you need to do. You need to apply this trick or this tool. And you can do extremely atomic level conversations. So because of Lean, I can collaborate, with dozens of people across the world, most of whom I have never met in person, and I may not know actually even whether they're how reliable they are in their in the proof they give me. But Lean gives me a certificate of trust. So I can do trustless mathematics.
So there's so many interesting questions. So one, you're known for being a great collaborator. So what is the right way to approach solving a difficult problem in mathematics when you're collaborating? Are you doing a divide and conquer type of thing, or are you focused on a particular part and you're brainstorming?
There's always a brainstorming process first. Yeah, so math research projects, sort of by their nature, when you start, you don't really know how to do the problem. It's not like an engineering project where somehow the theory has been established for decades and its implementation is the main difficulty. You have to figure out even what is the right path. So this is what I said about cheating first. It's like to go back to the bridge building analogy. So first assume you have infinite budget and like unlimited amounts of workforce and so forth. Now can you build this bridge? Okay. Now have infinite budget but only finite workforce. Right now can you do that and so forth? I mean, of course, no engineer can actually do this because they have fixed requirements. Yes, there's this sort of jam sessions always at the beginning where you try all kinds of crazy things and you make all these assumptions that are unrealistic, but you plan to fix later. And you try to see if there's even some skeleton of an approach that might work. And then hopefully that breaks up the problem into smaller sub-problems, which you don't know how to do, but then you focus on the sub ones. And sometimes different collaborators are better at working on certain things. So one of my theorems I'm known for is a theorem of Ben Green, which is now called the Green-Tao theorem. It's a statement that the primes contain arithmetic progressions of any length. So it was a modification of this theorem of Semeredi. And the way we collaborated was that Ben had already proven a similar result for progressions of length 3. He showed that just like the primes contain lots and lots of progressions of length 3, even subsets of the primes, certain subsets do. But his techniques only worked for length 3 progressions. They didn't work for longer progressions. But I had these techniques coming from ergodic theory, which is something that I had been playing with and I knew better than Ben at the time. And so if I could justify certain randomness properties of some set relating to the primes, like there's a certain technical condition which if I could have it, if Ben could supply me this fact, I could conclude the theorem. But what I asked was a really difficult question in number theory, which he said, no, there's no way we can prove this. So he said, can you prove your part of the theorem using a weaker hypothesis that I have a chance to prove it? And he proposed something which he could prove, but it was too weak for me. I can't use this. So there was this conversation going back and forth. It's sort of a
different cheats too.
Yeah. I want to cheat more. He wants to cheat less. Okay.
Yeah.
But eventually we found a property which A, he could prove, and B, I could use, and then we could prove our theorem. So there are all kinds of dynamics. I mean, it's every collaboration has some story. No two are the same.
And then on the flip side of that, like you mentioned with lean programming, now that's almost like a different story because you can create, I think you've mentioned a kind of a blueprint
right
for a problem, and then you can really do a divide and conquer with lean where you're working on separate parts.
Right.
And they're using the computer system proof checker essentially to make sure that everything is correct along the way.
So it makes everything compatible and trustable. So currently only a few mathematical projects can be cut up in this way. At the current state of the art, most of the lean activity is on formalizing proofs that have already been proven by humans. A math paper basically is a blueprint in a sense. It is taking a difficult statement like big theorem and breaking it up into maybe 100 little lemmas. But often not all written with enough detail that each one can be sort of directly formalized. A blueprint is like a really pedantically written version of a paper where every step is explained as much detail as possible, and to try to make each step kind of self-contained, or depending on only a very specific number of previous statements that have been proven, so that each node of this blueprint graph that gets generated can be tackled independently of the others, and you don't even need to know how the whole thing works. So it's like a modern supply chain. Like if you want to create an iPhone or some other complicated object, no one person can build a single object, but you can have specialists who just, if they're given some widgets from some other company, they can combine them together to form a slightly bigger widget.
I think that's a really exciting possibility because you can have, if you can find problems that could be broken down this way, then you can have, thousands of contributors, right?
Yes,
it could be completely distributed.
So I told you before about the split between theoretical and experimental mathematics. And right now, most mathematics is theoretical and only a tiny bit is experimental. I think the platform that Lean and other software tools, GitHub and things like that, they will allow experimental mathematics to scale up to a much greater degree than we can do now. So right now, if you want to do any mathematical exploration of some mathematical pattern or something, you need some code to write out the pattern. And I mean, sometimes there are some computer algebra packages that can help, but often it's just one mathematician coding lots and lots of Python or whatever. And because coding is such an error-prone activity, it's not practical to allow other people to collaborate with you on writing modules for your code, because if one of the modules has a bug in it, the whole thing is unreliable. So you get these bespoke spaghetti code written by not professional programmers, but by mathematicians, and they're clunky and slow, and so because of that, it's hard to really mass produce experimental results. But I think with Lean, I mean, so I'm already starting some projects where we are not just experimenting with data, but experimenting with proofs. So I have this project called the Equational Theories Project. Basically, we generated about 22 million little problems in abstract algebra. Maybe I should back up and tell you what the project is. Okay, so abstract algebra studies operations like multiplication and addition and their abstract properties. Okay, so multiplication, for example, is commutative. X times y is always y times x, at least for numbers. And it's also associative. X times y times z is the same as x times y times z. These operations obey some laws and they don't obey others. For example, x times x is not always equal to x. So that law is not always true. So given any operation, it obeys some laws and not others. And so we generated about 4,000 of these possible laws of algebra that certain operations can satisfy. And our question is, which laws imply which other ones? So for example, does commutativity imply associativity? And the answer is no, because it turns out you can describe an operation which obeys the commutative law but doesn't obey the associative law. So by producing an example, you can show that commutativity does not imply associativity. But some other laws do imply other laws by substitution and so forth. And you can write down some algebraic proof. So we look at all the pairs between these 4,000 laws, and there's about 22 million of these pairs. And for each pair, we ask, does this law imply this law? If so, give a proof. If not, give a counterexample. So 22 million problems, each one of which you could give to an undergraduate algebra student, and they had a decent chance of solving the problem. Although there are a few, of these 22 million, there are like 100 or so that are really quite hard. Okay, but a lot are easy. And the project was just to work out, to determine the entire graph, like which ones imply which other ones.
That's an incredible project, by the way. Such a good idea, such a good test of the very thing we've been talking about at a scale that's remarkable.
Yeah, so it would not have been feasible. I mean, the state of the art in the literature was 15 equations and sort of how they imply. That's sort of at the limit of what a human with pen and paper can do. So you need to scale it up. So you need to crowdsource, but you also need to trust all the. No one person can check 22 million of these proofs. You need it to be computerized, and so it only became possible with Lean. We were hoping to use a lot of AI as well. So the project is almost complete. So of these 22 million, all but 2 have been settled.
Wow.
And of those 2, we have a pen and paper proof of the 2, and we're formalizing it. In fact, this morning I was working on finishing it. So we're almost done on this.
It's incredible.
It's fantastic.
How many people were able to get?
About 50. Which in mathematics is considered a huge number.
It's a huge number. That's crazy.
Yeah. So we're going to have a paper with 50 authors and a big appendix of who contributed what.
Here's an interesting question, not to maybe speak even more generally about it. When you have this pool of people, is there a way to organize the contributions by level of expertise of the people, of the contributors? Now, okay, I'm asking you a lot of pothead questions here, but I'm imagining a bunch of humans and maybe in the future some AIs.
Yeah.
Can there be like an ELO rating type of situation where like a gamification of this?
The beauty of these Lean projects is that automatically you get all this data. So like everything's to be uploaded to this GitHub, and GitHub tracks who contributed what. So you could generate statistics from at any later point in time. You can say, oh, this person contributed this many lines of code or whatever. I mean, these are very crude metrics. I would definitely not want this to become like part of your tenure review or something. But I mean, I think already in enterprise computing, right, people do use some of these metrics as part of the assessment of performance of an employee. Again, this is a direction which is a bit scary for academics to go down. We don't like metrics so much.
And yet, academics use metrics. They just use old ones. Number of papers.
Yeah, it's true. It's true that, yeah, I mean,
It feels like this is a metric, while flawed, is going in the right direction, right?
yeah,
It's an interesting. I mean, at least it's a very interesting metric.
yeah, I think it's interesting to study. I mean, I think you can do studies of whether these are better predictors. There's this problem called Goodhart's law. If a statistic is actually used to incentivize performance, it becomes gamed, and then it is no longer a useful measure.
Oh, humans always
Yeah, no, I mean,
always gaming the
it's rational.
incentives.
So what we've done for this project is self-report. So there are actually these standard categories from the sciences of what types of contributions people give. So there's this concept and validation and resources and coding and so forth. So we there's a standard list of 12 or so categories. And we just ask each contributor to, there's a big matrix of all the authors and all the categories, just to tick the boxes where they think that they contributed. And just to give a rough idea, like, oh, so you did some coding and you provided some compute, but you didn't do any of the pen and paper verification or whatever. And I think that works out. Traditionally, mathematicians just order alphabetically by surname. So we don't have this tradition as in the sciences of, lead author and second author and so forth, which we're proud of. We make all the authors equal status, but it doesn't quite scale to this size. So a decade ago, I was involved in these things called polymath projects. It was the crowdsourcing mathematics, but without the lean component. So it was limited by, you needed a human moderator to actually check that all the contributions coming in were actually valid. And this was a huge bottleneck, actually. But still, we had projects that were, 10 authors or so. But we had decided at the time not to try to decide who did what, but to have a single pseudonym. So we created this fictional character called DHJ Polymath. In the spirit of Bourbaki is the pseudonym for a famous group of mathematicians in the 20th century. But and so the paper was authored under pseudonym, so none of us got the author credit. This actually turned out to be not so great for a couple of reasons. So one is that if you actually wanted to be considered for tenure or whatever, you could not use this paper in your as you submitted as one of your publications, because you didn't have the formal author credit. But the other thing that we've recognized much later is that when people referred to these projects, they naturally refer to the most famous person who was involved in the project. Oh, so this was Tim Gower's polymath project. Mm-hmm. This was Terence Tao's polymath project, and not mention the other 19 or whatever people that were involved.
Yeah.
So we're trying something different this time around, where we have everyone's an author, but we will have an appendix with this matrix. And we'll see how that works.
I mean, so both projects are incredible. Just the fact that you're involved in such huge collaborations. But I think I saw a talk from Kevin Buzzard about the lean programming language just a few years ago, and you're saying that this might be the future of mathematics. And so it's also exciting that you're embracing one of the greatest mathematicians in the world, embracing this, what seems like the paving of the future of mathematics. So I have to ask you here about the integration of AI into this whole process. So DeepMind's Alpha Proof was trained using reinforcement learning on both failed and successful formal lean proofs of IMO problems.
Yes,
so this is sort of high level high school.
Oh, very high level, yes.
Very high level high school level mathematics problems. What do you think about the system, and maybe what is the gap between this system that is able to prove the high school level problems versus graduate level problems?
Yeah, the difficulty increases exponentially with the number of steps involved in the proof. It's a combinatorial explosion. Right? So the thing with large language models is that they make mistakes. And so if a proof has got 20 steps and your large language model has a 10% failure rate at each step of going in the wrong direction, it's just extremely unlikely to actually reach the end.
Actually, just to take a small tangent here, how hard is the problem of mapping from natural language to the formal program?
Oh, yeah, it's extremely hard, actually. Natural language, it's very fault tolerant. Like you can make a few minor grammatical errors and a speaker in the second language can get some idea of what you're saying. But formal language, if you get one little thing wrong, I think that the whole thing is nonsense.
Got it.
Even formal to formal is very hard. There are different incompatible proof assistant languages. There's Lean, but also Coq and Isabelle and so forth. And actually, even converting from a formal language to formal language is an basically unsolved problem.
That is fascinating. Okay, so but once you have an informal language, they're using their RL trained model, so something akin to AlphaZero that they use for
Yes.
Go, to then try to come up with proofs. They also have a model, I believe it's a separate model for geometric
Yes.
problems. So, what impresses you about this system, and what do you think is the gap?
Yeah. We talked earlier about things that are amazing over time become kind of normalized. So now somehow it's, of course, geometry is a solvable problem.
Right, that's true. That's true. I mean, it's still beautiful to
No,
look at the work they're doing.
these are great works. It shows what's possible. I mean, the approach doesn't scale currently. 3 days of Google's server time to solve one high school math problem. This is not a scalable prospect, especially with the exponential increase in as the complexity increases.
We should mention that they got a silver medal performance.
The equivalent of, I mean,
Equivalent of a
I
silver
mean,
medal performance.
so first of all, they took way more time than was allotted, and they had this assistance where the humans helped by formalizing. But also they're giving themselves full marks for the solution, which I guess is formally verified. So I guess that's fair. Um, yeah. There are efforts. There will be a proposal at some point to actually have an AI math Olympiad where, at the same time as the human contestants get the actual Olympiad problems, AIs will also be given the same problems with the same time period, and the outputs will have to be graded by the same judges, um, and which means that it will have to be written in natural language rather than formal language.
Oh, I hope that happens. I hope
Yeah.
that this IMO happens. I hope next one.
It won't happen this IMO. The performance is not good enough in the time period, but there are smaller competitions. There are competitions where the answer is a number rather than a long form proof, and that's AIs are actually a lot better at problems where there's a specific numerical answer, because it's easy to reinforcement learning on it. Yeah, you got the right answer, you got the wrong answer. It's a very clear signal. But a long form proof either has to be formal, and then the Lean can give it thumbs up, thumbs down, or it's informal. But then you need a human to grade it to tell. And if you're trying to do billions of reinforcement learning, runs, you can't hire enough humans to grade those. I mean, it's already hard enough for the large language models to do reinforcement learning on just the regular text that people get. But now if you actually hire people, not just give thumbs up, thumbs down, but actually check the output mathematically, that's too expensive.
So if we just explore this possible future, what is the thing that humans do that's most special in mathematics? So that you could see AI not cracking for a while. So inventing new theories, so coming up with new conjectures versus proving the conjectures,
Right.
building new abstractions, new representations, maybe an AI Terence Tao with seeing new connections between disparate fields.
It's a good question. I think the nature of what mathematicians do over time has changed a lot. Um, so 1,000 years ago, mathematicians had to compute the date of Easter, and there's really complicated calculations. But it's all been automated for centuries. We don't need that anymore. They used to do spherical navigation, spherical trigonometry to navigate how to get from the old world to the new, or something. Very complicated calculations, again, been automated. Even a lot of undergraduate mathematics, even before AI, like Wolfram Alpha, for example, it's not a language model, but it can solve a lot of undergraduate level math tasks. So on the computational side, verifying routine things like having a problem and say, here's a problem in partial differential equations. Could you solve it using any of the 20 standard techniques? And they say, yes, I've tried all 20, and here are the 100 different permutations, and here's my results. And that type of thing, I think it will work very well. Type of scaling to once you solve one problem to make the AI attack 100 adjacent problems. The things that humans do still, so where the AI really struggles right now is knowing when it's made a wrong turn. That it can say, "Oh, I'm going to solve this problem. I'm going to split up this problem into these two cases. I'm going to try this technique." And sometimes, if you're lucky and it's a simple problem, it's the right technique, and you solve the problem. And sometimes it will have a problem. It would propose an approach which is just complete nonsense. But like it looks like a proof. So this is one annoying thing about LLM generated mathematics. So um,
Yeah.
we've had human generated mathematics as very low quality. Like submissions of people who don't have the formal training and so forth. But if a human proof is bad, you can tell it's bad pretty quickly.
Mm-hmm.
It makes really basic mistakes. But the AI generated proofs, they can look superficially flawless. And it's partly because that's what the reinforcement learning has actually trained them to do, to make things, to produce text that looks like what is correct, which for many applications is good enough. So the errors are often really subtle, and then when you spot them, they're really stupid. Like no human would have actually made that mistake.
Yeah, it's actually really frustrating in the programming context because I program a lot, and yeah, when a human makes low quality code, there's something called code smell, right? You can
Yes,
tell,
yeah, yeah,
immediately, like,
right,
okay,
yeah,
there's
yeah.
signs. But with AI generate code,
They're odorless.
and then you're right.
Yeah,
Eventually, you find an obvious dumb thing that just looks
yeah,
like good code.
yeah. So
It's very tricky to and frustrating for some reason to
yeah,
to
so
have to work.
yeah, so the sense of smell. Okay, there you go.
Yes, yes.
This is one thing that humans have, and there's a metaphorical mathematical smell that
Yeah.
uh, it's not clear how to get the AIs to duplicate that. Eventually, I mean, so the way AlphaZero and so forth to make progress on Go and chess and so forth is in some sense they have developed a sense of smell for Go and chess positions.
Mhm.
That this position is good for white, this is good for black. They can't enunciate why, but just having that sense of smell lets them strategize. So if AIs gain that ability to sort of a sense of viability of certain proof strategies, so you can say, I'm going to try to break up this problem into two small subtasks, and they can say, oh, this looks good. The two tasks look like they're simpler tasks than your main task, and they still got a good chance of being true. So this is good to try. Or no, you made the problem worse because each of the two subproblems is actually harder than your original problem, which is actually what normally happens if you try a random thing to try. It's very easy to transform a problem into an even harder problem.
Mhm.
Very rarely do you transform to a simpler problem. Yeah, so if they can pick up a sense of smell, then they could maybe start competing with human level mathematicians.
So this is a hard question, but not competing, but collaborating.
Yeah.
Okay, hypothetical. If I gave you an oracle that was able to do some aspect of what you do and you could just collaborate with it,
Yeah.
what would you like that oracle to be able to do? Would you like it to maybe be a verifier, like check,
Mhm.
do the code smell, like yes,
Yeah.
Professor Tao, this is a promising, fruitful direction.
Yeah.
Or would you like it to generate possible proofs and then you see which one is the
Mhm.
right one? Or would you like it to maybe generate different representation, totally different ways of seeing this problem?
Yeah. I think all of the above. A lot of it is we don't know how to use these tools because it's a paradigm that it's not. Um, yeah, we have not had in the past assistants that are competent enough to understand complex instructions
Mhm.
that can work at massive scale, but are also unreliable. Like it's an interesting, but unreliable in subtle ways, was providing sufficiently good output. It's an interesting combination. I mean, you have like graduate students that you work with who kind of like this, but not at scale. And we had previous software tools that can work at scale, but very narrow. So we have to figure out how to use. So Tim Gowers actually, you mentioned, he actually foresaw, like in 2000, he was envisioning what mathematics would look like in actually 2.5 decades. Actually. And
That's funny.
yeah, he wrote in his article a hypothetical conversation between a mathematical assistant of the future and himself. He's trying to solve a problem, and they would have a conversation. Sometimes the human would propose an idea, and the AI would evaluate it. And sometimes the AI would propose an idea, and And sometimes a computation was required, and AI would just go and say, okay, I've checked the 100 cases needed here, or the first, you said this is true for all n, I've checked it for n up to 100, and it looks good so far, or hang on, there's a problem at n equals 46. Yeah, so just a free-form conversation where you don't know in advance where things are going to go, but just based on I think ideas get proposed on both sides, calculations get proposed on both sides. I've had conversations with AI where I say, okay, we're going to collaborate to solve this math problem. And it's a problem that I already know the solution to. So I try to prompt it. Okay, so here's the problem. I suggest using this tool. And then it'll find this lovely argument using a completely different tool, which eventually goes into the weeds and say, no, try using this. Okay, and it might start using this, and then it'll go back to the tool that it wanted to do before. And like you have to keep railroading it onto the path you want. And I could eventually force it to give the proof I wanted. But it was like herding cats. And the amount of personal effort I had to take to not just sort of prompt it, but also check its output, because like a lot of what it looked like it's going to work. Oh no, there's a problem on line 17, and basically arguing with it. Like it was more exhausting than doing it unassisted. So but that's the current state of the art.
I wonder if there's a phase shift that happens to where it's no longer feels like herding cats, and maybe you'll surprise us how quickly that comes.
I believe so. So in formalization, I mentioned before that it takes 10 times longer to formalize a proof than to write it by hand. With these modern AI tools, and also just better tooling, the lean developers are doing a great job adding more and more features and making it user-friendly. It's going from 9 to 8 to 7. Okay, no big deal. But one day it will drop below 1. And that's a phase shift, because suddenly it makes sense when you write a paper to write it in lean first, or through a conversation with AI who's generating lean on the fly with you. And it becomes natural for journals to accept, maybe they'll offer expedite refereeing. That if a paper has already been formalized in lean, they'll just ask the referee to comment on the significance of the results and how it connects to literature, and not worry so much about the correctness, because that's been certified. Papers are getting longer and longer in mathematics, and it's harder and harder to get good refereeing for the really long ones, unless they're really important. It is actually an issue, and the formalization is coming in at just the right time for this to be.
And the easier and easier it gets because of the tooling and all the other factors,
Right.
then you're going to see much more, like math lib will grow potentially exponentially.
Yeah.
It's a virtuous cycle. Okay.
I mean, one phase shift of this type that happened in the past was the adoption of LaTeX. So LaTeX is this typesetting language that all mathematicians use now. So in the past, people used all kinds of word processors and typewriters and whatever. But at some point, LaTeX became easier to use than all other competitors, and people would just switch, within a few years. Like it was just a dramatic phase shift.
It's a wild out there question, but what year? How far away are we from a AI system being a collaborator on a proof that wins the Fields Medal? So that level.
Okay. Well, it depends on the level of collaboration. I mean,
no, like it deserves to get the Fields Medal. Like, so half and half.
Already, like I can imagine a Fields Medal winning paper having some AI assistance in writing it. Like the autocomplete alone is already. I use it, like it speeds up my own writing. Like you can have a theorem, and you have a proof, and the proof has 3 cases, and I write down the proof of the first case, and the autocomplete just suggests, now here's how the proof of the second case could work, and like it was exactly correct. That was great. Saved me like 5-10 minutes of typing.
But in that case, the AI system doesn't get the Fields Medal.
No.
Are we talking 20 years, 50 years, 100 years? What do you think?
Okay. So I gave a prediction in print, so by 2026, which is now next year, there will be math collaborations, with AI. So not Fields Medal winning, but like actual research level math papers.
Like published ideas that are in part generated by AI.
Maybe not the ideas, but at least some of the computations, the verifications. Yeah, I mean,
has that already happened?
Has already happened. Yeah, there are problems that were solved by a complicated process, conversing with AI to propose things, and the human goes and tries it, and the contract doesn't work. But it might propose a different idea. It's hard to disentangle exactly. There are certainly math results which could only have been accomplished because there was a human mathematician and an AI involved. But it's hard to sort of disentangle credit. I mean, these tools, they do not replicate all the skills needed to do mathematics, but they can replicate sort of some non-trivial percentage of them, 30, 40%. So they can fill in gaps. So coding is a good example. So it's annoying for me to code in Python. I'm not a native, I'm not a professional programmer. But with AI, the friction cost of doing it is much reduced. So it fills in that gap for me. AI is getting quite good at literature review. I mean, there's still a problem with hallucinating, references that don't exist. But this, I think, is a solvable problem. If you train in the right way and so forth, you can and verify. Using the internet. You should in a few years get to the point where you have a lemma that you need, and say, has anyone proven this lemma before? And it will do basically a fancy web search AI assistant and say, yeah, there are these 6 papers where something similar has happened. And I mean, you can ask it right now, and it will give you 6 papers, of which maybe 1 is legitimate and relevant, 1 exists but is not relevant, and 4 are hallucinated. It has a non-zero success rate right now, but there's so much garbage, the signal-to-noise ratio is so poor that it's most helpful when you already somewhat know the literature, and you just need to be prompted to be reminded of a paper that was already subconsciously in your memory.
Versus helping you discover you were not even aware of, but is the correct citation.
Yeah, that it can sometimes do, but when it does, it's buried in a list of options for which the other
that are bad.
Yeah,
I mean, being able to automatically generate a related work section that is correct.
Yeah.
That's actually a beautiful thing that might be another phase shift because it assigns credit correctly.
Yeah.
It breaks you out of the silos of
No,
thought,
Yeah, no, but there's a big hump to overcome right now. I mean, it's like self-driving cars.
Right.
The safety margin has to be really high for it to be feasible. So there's a last mile problem with a lot of AI applications that they can develop tools that work 20%, 80% of the time, but it's still not good enough. And in fact, even worse than good in some ways.
I mean, another way of asking the Fields Medal question is, what year do you think you'll wake up and be like real surprised? You read the headline, the news of something happened that AI did, like, real breakthrough, something. It doesn't, like Fields Medal, even hypothesis. It could be like really just this alpha zero moment would go, that kind of thing.
Right. This decade, I can see it like making a conjecture between two things that people thought was unrelated.
Oh, interesting. Generating a conjecture that's a beautiful conjecture.
Yeah, and actually has a real chance of being correct and meaningful. And
because that's actually kind of doable, I suppose. But where the data is, no, that would be truly amazing. Yeah.
The current models struggle a lot. I mean, so a version of this is, the physicists have a dream of getting the AIs to discover new laws of physics. The dream is you just feed it all this data, okay, and this is here is a new patent that we didn't see before. But it actually even struggles. The current state of the art even struggles to discover old laws of physics from the data. I mean, or if it does, there's a big concern of contamination. That it did it only because, like, somewhere in this training data, it already somehow knew, Boyle's law or whatever law you're trying to reconstruct. Part of it is that we don't have the right type of training data for this. So for laws of physics, like we don't have like a million different universes with a million different laws of nature. Like a lot of what we're missing in math is actually the negative space of. So we have published things that people have been able to prove, and conjectures that ended up being verified, or maybe counterexamples produced. But we don't have data on things that were proposed, and they're kind of a good thing to try. But then people quickly realized that it was the wrong conjecture, and then they said, "Oh, but we should actually change our claim to modify it in this way to actually make it more plausible." There's a trial and error process, which is a real integral part of human mathematical discovery, which we don't record because it's embarrassing. We make mistakes, and we only like to publish our wins. And the AI has no access to this data to train on. I sometimes joke that basically the AI has to go through a grad school and actually, go to grad courses, do the assignments, go to office hours, make mistakes, get advice on how to correct the mistakes, and learn from that.